Today, in this video, we are going to learn how to apply our knowledge of exponential functions to some modelling. So as you can see here, I've got quite a few notes in front of you on the screen. Before I read through those notes with you, I'm just going to remind you of what an exponential graph looks like. So this is a basic exponential graph, and because we're talking about applications here, anything where the graph goes up like this, we would class that as growth. And what that usually means is it's growth over some particular time. So some examples that we might be using for growth are growth of cells, population growth, even compound interest, growth of money. And if we were graphing this, on the x-axis usually would be time. Time is what goes along the x-axis. We're also going to look at some exponential decay. Now, if I look at decay, you've got to appreciate this graph could move along the x-axis, but usually decay means that we're looking at some kind of model going down. So this is an example of a graph that goes down. Examples of decay are radioactive decay, or materials that are cooling, where there's temperature up this side, and obviously time would be along the x-axis. Alright, so exponential growth and decay can be modelled using these exponential equations. So I'm just going to talk through this because you won't have seen this equation before. A and B and T are just variables. So let's just talk through what they are. So obviously A would be the thing here that would be on the y-axis. So I just talked about temperature. It could be T, it could be anything. A0 is what we call the initial quantity. B is our base normally when we're talking about exponential functions, but in this case, B is our growth or our decay factor. For our applications, B is always a positive number. T is a time quantity, so how much time. Now, depending on whether it's growth or decay, depends on the growth factor here, B. So if B is greater than 1, then we are modelling growth. If B is between 0 and 1, then we are modelling decay. So what we're going to do in the syllabus is we're going to talk about specific examples where we're using this kind of formula. And obviously, like I said, the variables change. So the first one is cell growth. So cell growth is where a cell divides into 2 new cells after a set amount of time. And we can model this using this equation here. So if we look at this, we can see that N0 is our initial value. So you might say at the beginning of the bacterial population, there were 5,000 cells. So we would say that 5,000 is N0. 2 is our growth factor, and then this power here, T divided by capital TD, this is our power. And in this case, the power represents the generation time. So we've got, or T divided by the generation time, and the generation time is how many minutes before each cell splits. So I'm going to do a specific example using this model here. So what we've got here is, what is the generation time of a bacterial population that increases from 5,000 cells to 100,000 cells in just 4 hours of growth? So if we think about this question, we're going to define what each of the variables that we know are, and then obviously then we'll go through a process once we sub the values in to solve for TD, because TD, this part here, is our generation time. So what we do know is that the initial bacterial population was 5,000. So N0 is 5,000. We also know that it grew to 100,000. So N at this particular time after 4 hours is 100,000. We need to have the time in minutes because it's defined in minutes. So we need to convert 4 hours into minutes, 240 minutes. So T, small t, is the time. That's 240 minutes. And then it's TD is what we're trying to find. So once I've defined my variables, I'm going to just substitute them into this formula here and go through and solve it. So I'm actually going to use, I've already written up these notes here, so I'm just going to scroll up. It's having trouble scrolling up at the moment. Give me a sec. Alright, so I've written in that value, the values from the formula. Now, the next thing I'm going to do is divide by 5,000. Both sides, so I'm left with this step. Then I'm going to then write my equivalent, or use the equivalence relationship for to convert this into a log. So taking the equivalence relationship, we know that that's equivalent to log base 2 of 20 equals 240 over TD. I can now do some rearranging, take the TD up here and take log to the base 2 of 20 down here and solve using a calculator. If you look over on the left hand side, you can see this is where I have defined the variables before substituting them into the formula. I'm now going to look at how we might check that this is a reasonable answer. So if I have a look at this, we can go through and work out that if the generation time is 55 minutes, which is what we've got up here, we can just then work out, well, and what those would be N0, N1, N2, N3, N4, just by using this formula up here. And we can work out that it comes to 3 hours 40 minutes. So therefore, we're likely to be at 100,000 in the next 20 minutes, because that's a perfectly reasonable answer. So obviously you can see it's doubling each time, 55 minutes each time, add another 20 minutes, and we're going to be at least at 100,000. So it's a reasonable answer. All right, let's look at another application of exponential equations. We've talked about decay, so let's look at radioactive decay. Radioactive decay is where radioactive material reduces in size. Again, the amount present is dependent on the time that has elapsed. So this is a rule that we generally use. Now, it's very similar to the previous one, where A0 is the initial, 2 is our decay factor, and then our power is negative kT, and K is the constant that varies from material to material. Often we talk about half-life, and when we're talking about radioactive decay, the half-life is the time it takes for half of the material to decay. So let's run into an example. So after 1,000 years, a sample of radium-226 has decayed to 64.7% of its original mass. Find the half-life of radium-226. So what I'm going to do in this case is work out, well, if the time that we've been given is 1,000, so lowercase t is 1,000, the quantity is 64.7% of the initial value, but I don't know what the initial value is. So I need to convert this percent into a decimal and multiply it by A0 to get A. So that's pretty much written there like so. So we've got A now. Now when I substitute A, the left-hand side, into the formula, I'm going to have here 0.647 A0, and on the right-hand side I'm going to have A0 times 2 minus K times 1,000, or sorry, negative 1,000. So we do that. Now, dividing through both sides by A0, because they cancel out because they're on both sides, I'm left with 0.647 equals 2 to the power negative 1,000 K. Now I can now put my equivalence rule in there, or you can in fact take log to the base 10 of both sides. We have met taking logs of both sides before when we were looking at solving geometric sequences. So it is possible to do it another way. So if we take logs to the base 10 of both sides, taking logs of both sides we call it, then all I do is put log in front of each of the things I'm going to do. The next step is then using that special log law where we take the power down, which we learnt when we did geometric sequences, and then rearranging it to get K as the subject, because it's K that we need to find. And when we solve that, we get K, which is our constant, as 0.000628. Now, let's go back to our formula, which we have here on the right-hand side. I can sub K back in there now, and I'm left with this. And therefore, the only unknowns in this case are A0 and T. However, if I read this question again, I'm looking for the half-life. So I want half of the initial value, and we don't know what that initial value is, but I know I want half of it. So let's define now A as half of A0. As so. All right, now I'm going to now put this in as A on the left-hand side of the formula, and I'm going to follow the same method as I did up above. So doing that, A0's cancel out. We're dividing both sides by A0. I'm left with this here. So now the only unknown I've got to solve is T, so I can find out at what time I got the half-life, or half the quantity. So taking logs of both sides and then pulling down that power to the front, as we did when we did geometric sequences, And solving to rearrange for t, I get t as 1592.36. That means the half-life is approximately 1592 years. That's almost 1600 years. And that's where I'm going to leave it because this is a 10-minute video.